steam power plant. 1 to 2 pump, water pumped, then boiler, steam expands in turbine, WT, condenser, heat exchanged, cooling water in, out, cooling tower. Condenser is an essential equipment of steam power plant. If no condenser is used, steam expanded to atmospheric pressure, then temperature will be 100, then temperature of steam will be 100 degrees centigrade. This energy will be wasted. If condenser is used, then steam can expand up to very low pressure and temperature, which will increase turbine work, whereas heat input is same, so efficiency of cycle is increased. Vapor power cycle, working fluid changes its phase during the cycle. Ideal vapor power cycle, Carnot vapor power cycle, TS, TH, TL, it will be box like before, 1, 2, 3, 4, 1 Q in QR constant temperature, TL is equal to T sat at PL, TH is equal to T sat at PL, efficiency is equal to 1 minus TL by TH is equal to W net by Q in, W net is equal to Q in into 1 minus TL by TH is equal to HL is equal to H3 minus H2, Hg at pH, Hf at pH into 1 minus TL by TH. Limitation of Carnot vapor power cycle, it is very difficult to design and control partial condenser. It is very difficult to design a device which increases pressure of mixture as the complete expansion takes place within the vapor dome, so the quality of steam at exit of turbine is very poor, which may create wear and tear in turbine. Rankine cycle, TS 1 to 2 1 to 2 no 1 2 3 4 1 Carnot vapor power cycle, 1 prime 2 prime 3 prime 4 prime 1 prime Rankine cycle without superheat, 1 prime 2 prime 3 double prime 4 double prime 1 prime Rankine cycle with superheat. Comparison of Rankine cycle with Carnot vapor power cycle, thermal efficiency, WTR is equal to WTC. WPR less than WPC, W net Rankine greater than W net C, efficiency eta Carnot greater than eta Rankine, eta is equal to W net by Q in, both increased. Carnot TMA is equal to Tmax, Rankine TMA less than Tmax. Efficiency of Carnot cycle is greater than Rankine cycle because mean temperature of heat addition is more than Rankine cycle, whereas heat rejection is same. Work ratio, it is defined as ratio of net work to positive turbine work. The work ratio is equal to W net by WT, WT Rankine is equal to WT Carnot, W net Rankine greater than W net Carnot, W work ratio Rankine greater than work ratio Carnot. A plant with higher work ratio is preferable. The work ratio of Rankine cycle is highest among all power plants because it uses pump which consumes very less work. The work ratio of gas turbine cycle is 0.4 to 0.6. It means 40 to 60% of turbine work is consumed by compressor. The work ratio of Rankine cycle is 0.96 to 0.98. It means 2 to 4% of turbine work is consumed by pump. Back work ratio, it is defined as ratio of negative work to the positive turbine work. Back work ratio is equal to W negative by W positive. The work done by turbine Carnot is equal to work done by turbine Rankine, work done by compressor Carnot greater than work done by pump Rankine. Back work ratio of Rankine less than back work ratio of Carnot. W net by W positive is equal to W positive by W positive minus W negative by W positive. Work ratio is equal to 1 minus back work ratio. Work ratio plus back work ratio is equal to 1. Specific steam consumption, it is defined as a mass flow rate of steam required to produce unit power. SSC is equal to ms dot by power. SSC is equal to ms dot by ms dot into W net. Kg per second, kg per second into kilojoule per kg. SSC is equal to 1 by W net kg per kilojoule hour by hour. The SSC is equal to 3600 by W net kg per kilowatt hour. Specific steam consumption represents the size of power plant. If specific steam consumption is less, it means less amount of steam required for to produce given power. So plant size is small. Analysis of Rankine cycle TS 1 to 2, 2 to 3, 3 to 4. P in boiler pressure, PL condenser pressure. 1 to 2 reversible adiabatic in pressure in pump volume constant h1 is equal to hf increases pressure in pump volume, but volume constant h1 is equal to hf at PL condenser pressure. W open is equal to minus integral 1 to 2 VdP. W pump is equal to V into P2 minus P1. First law in pump H1 plus Q is equal to H2 plus W. H2 is equal to H1 plus WP. 2 to 3 constant pressure. Heat addition in boiler H3 is equal to H super at P and T superheat. First law in boiler H3 plus Q is equal to H3 plus W. Q positive, W 0. Q in is equal to H3 minus H2. 3 to 4. Reversible adiabatic expansion in turbine S3 is equal to S super at a Pn and T super at 2 superheat. S4 is equal to S3. SF is equal to X4 into Sg minus SF is equal to S3 at PL. X4 is equal to, we can get it, H4. Then from that H4 is equal to HF plus X into Hg minus HL. From that H4 we can get first line turbine H3 plus Q is equal to H4 plus W. W is positive, Q 0. WT is equal to H3 minus H4. W net is equal to WT minus WP. Efficiency is equal to W net by Qn. SSC is equal to 3600 by W net. Power is equal to ms dot by into W net. Ms dot is equal to power by W net. 4 to 1 constant pressure heat rejection in condenser. First law H4 plus Q is equal to H1 plus W. W 0. QR is equal to H4 minus H1. Energy balance in condenser ms dot into H1 minus H4 is equal to mw dot into Cw into T2 prime minus T1 prime. Methods to improve performance of Rankine cycle: increase boiler pressure. If we increase 2 prime, 3 prime, 4 prime, 1 prime, WT is equal to H3 minus H4. H3 decreases, H4 decreases more. H4 decreases more. So H3 is equal to H super 8 at this is an example. From this we can say W pump almost same as a small increase. W turbine increases, HF is equal to HF plus X4 into Hg minus HF at PL. W net is equal to WT minus WP. W net increases, Q in decreases. W net increases, Q in decreases. Efficiency increases, specific steam consumption decreases as W net increased. Quality of steam decreases. Boiler pressure is decided by quality of steam at exit of turbine. Decrease in condenser pressure. W turbine increases, WP almost same. W net increases, Q in increases, because 2 prime to 3 prime, Wn efficiency is equal to W net by Qn. Efficiency increases, quality of steam decreases, P condenser decreases, Ti decreases, leakage due to low pressure. Superheating, W turbine increases, W pump remains same, W net increases, Qn increases. Efficiency is equal to W net by Qn, both increases, efficiency increases. Quality of steam increases. Maximum temperature in the cycle is decided by metallurgical condition of the system. Reheating, TS, pH PV reheating. Reheating in Rankine cycle, reheating is basically to get benefit of high boiler pressure. It increases dryness fraction at exit of turbine. 1, 2, 3, 4 prime 1 simple Rankine cycle. 1, 2, 3, 4, 5, 6, 1 reheat Rankine cycle. H1 is equal to HF at PL. WP is equal to V1 into P2 minus P1. H2 is equal to H1 plus WP. S3 is equal to S super plus at H3 is equal to H super at PH and PL. H5 is equal to H superheat. S4 is equal to S3. S6 is equal to S5. Finally, W turbine is equal to WH. From that X4, X6 we can get. From that H4, H6 we can get. W turbine is equal to WH high pressure turbine plus W low pressure turbine is equal to H3 minus H4 plus H5 minus H6. W net is equal to W turbine minus W pump. Q in is equal to H3 minus H2 plus H5 minus H4. Efficiency is equal to W net by Q in. Power is equal to ms dot into W net. Ms dot is equal to power by W net. Specific steam consumption is equal to 3600 by W net kg per kilowatt hour. Comparison of reheat Rankine cycle with simple Rankine cycle. Case 1, case 2. W turbine is increases, W pump same, Qin increases. Efficiency is equal to W net by Q9. Both increases. Due to reheating, efficiency may increase, decrease, or decrease depending on mean temperature of heat addition. But if steam expands more in first turbine, then mean temperature of heat addition decreases and efficiency also decreases. If in most practical cases, steam expands slightly on first turbine, so mean temperature of heat addition increases, so efficiency increases, quality of steam also increases. If it is like this, then efficiency increases. Regeneration in Rankine cycle. High pressure turbine, low pressure turbine, high pressure turbine, Y kg is bled off. Low pressure turbine, 1 minus Y kg flows through low pressure turbine. It is mixed with, after condenser, it is mixed in feed water heater, then passed through a pump. This will pass through one pump, this will pass through one pump. 1 2 prime 5 7 1 simple Rankine cycle. 1 2 3 4 5 6 7 1 regenerative Rankine cycle. W turbine is equal to 1 into H5 minus H6 plus 1 minus Y into H6 minus H7. W pump is equal to WP1 plus WP2 is equal to 1 minus Y into H2 minus H1 plus 1 into H4 minus H3. W net is equal to W turbine minus W pump. Qin is equal to H5 minus H4. Energy balance in feed water heater. Y kg steam 6 Y 1 minus Y kg water from 2 3 Y kg Y kg 1 kg water. Y H6 plus 1 minus Y H2 is equal to H3. Efficiency is equal to W net by Qn. SSC is equal to 3600 by W net. Comparison of regenerative cycle with simple Rankine cycle. W turbine decreases, W pump almost same. W net decreases, Qn decreases. Efficiency is equal to W net by Qn. Both decreases, efficiency increases. The efficiency of cycle increases due to regeneration because mean temperature of heat addition increases, whereas mean temperature of heat rejection remains same. Thermodynamic relations, principle of exact differential. Z is equal to f of xy, dz is equal to dou z by dou x into dA, dou z by dou x at constant y into dx plus dou z by dou y x into dy. compare with dz is equal to mdx plus ndy. M is equal to dou z by dou x at constant y, n is equal to dou z by dou y at constant x. Dou m by dou y is equal to dou by dou y of dou z by dou x at y. Dou n by dou x at y is equal to dou by dou x of dou z by dou y at x. If z is exact differential, dou m by dou y at x constant x is equal to dou n by dou x at constant y. Condition for exact differential. Properties are exact differentials. Maxwell's relations, we know TdS is equal to du plus pdv. Du is equal to TdS minus pdv. Compare with dz is equal to mdx plus ndy. M is equal to t, n is equal to minus p. Dx is equal to ds, dy is equal to dv. We know u is exact differential. Dou t by dou v is equal to minus dou p by dou s at constant volume. First Maxwell equation. We know TdS is equal to dh minus vdp. dh is equal to TdS plus vdp. M is equal to t, n is equal to v. Dx is equal to ds, dy is equal to dp. Dou t by dou p at constant s is equal to dou v by dou s at constant p. Gibbs function g is equal to h minus ts, dg is equal to dh minus sdt minus tds. dg is equal to tds plus vdp minus sdt minus tds. dg is equal to vdp minus sdt. Compare with dz is equal to mdx plus ndy. M is equal to v, n is equal to minus s, dx is equal to dp, dy is equal to dt. G is property dou v by dou t at constant pressure is equal to minus dou s by dou p at constant temperature. Helmholtz function f is equal to u minus ts. F is equal to u minus ts. Df is equal to du minus sdt minus tds. Df is equal to tds minus pdv minus sdt minus tds. Df is equal to minus pdv minus sdt. M is equal to minus p, n is equal to minus s, dx is equal to dv, dy is equal to dt. F is property dou p by dou t at constant pressure is equal to dou s by dou v at constant temperature. To remember all these, Pawans are very talented. PSVT, anti-clockwise PSVT, dou S by dou V at constant temperature is equal to dou P by dou T at constant volume. And dou S again, dou S by dou s by dou p at constant temperature is equal to dou v by dou t at constant pressure. Minus will be there. Again, dou t by dou v, dou t by dou v, dou t by dou v is equal at constant s is equal to dou s by dou p at const dou p by dou s at constant v. In if these two sides are negative, these two sides positive, these two sides lines comes positive. Dou t by dou p, dou t by dou p at constant s, dou v by is equal to dou v by dou s at constant p. Principle of exact differential, partial derivative theorem, cyclic relation. F of x comma y comma z is equal to 0. X is equal to f dash of y comma z. Y is equal to f dash of z comma x. Z is equal to f dash of x comma y. Dz is equal to dou z by dou x y at y into dx plus dou z by dou y x at dy. Dy is equal to dou y by dou z x at dz plus dou y by dou x dx. Dz is equal to dou z by dou x y dx plus dou z by dou y x into dy by dou y by dou z at x into dz plus dou y by dou x z into dx. Dz is equal to dou z by dou x at y plus dou z by dou y at x plus dou into finally dou z by dou x at y after writing also, then dou x by dou y into dou y by dou z into dou z by dou x at constant z x y respectively in multiplication equal to -1. Cyclic relation. For our thermodynamic relation, cyclic relation can be pvt dou p by dou v at constant temperature into dou v by dou t at constant pressure into dou t by dou p at constant volume is equal to -1. For ideal gas, we can prove that after multiplying everything we will get -1. TDS relation S is equal to f of t comma v. TDS is equal to dou s by dou v into dv plus dou s by dou t into dt. From dou s by dou t at v is cv by t, dou s by dou v at t is dou p by dou t. If from Maxwell relation, TDS is equal to cv dt plus t dou p by dou t, dou p by dou t into dv at constant volume into dv. Case 2, s is equal to f of t comma p, ds is equal to dou s by dou t at constant pressure into dt plus dou s by dou p at constant temperature into dp. dt by ds at constant pressure is equal to t by cp. dou s by dou p at constant temperature is equal to minus dou v by dou t at constant pressure. tds is equal to cp dt minus t dou v by dou t into dp minus t dou v by dou t into dp. Similarly, t is equal to f of p comma v. Also, we can write like this. Then, by equating ds of both, we will finally get dt is equal to t by cp minus cv into dou v by dou t into dp plus t by cp minus cv into dou p by dou t into dv. T is equal to function of p comma v. T is equal to dou t by dou p v into dp plus dou t by dou v into dv. Equation 3 and 4, t by cp minus cv into dou v by dou t at pressure is equal to dou t by dou p at constant volume. Cp minus cv is equal to t dou v by dou t at constant pressure into dou p by dou t at constant volume. We know that dou p by dou v into dou v by dou t into dou t by dou p is equal to -1. Substitute dou p by dou t at constant volume with this. Then we will get cp minus cv is equal to minus t dou v by dou t whole square into dou p by dou v. Dou p by dou v will be negative at constant temperature, will be negative. This will be positive, this will be positive. Overall cp minus cv will be positive. Cp minus cv is equal to minus t dou v by dou t whole square into dou p by dou v at constant temperature, Pt. Cp minus Cv is equal to positive, Cp greater than Cv, gamma is equal to Cp by Cv, gamma greater than 0, gamma greater than 1, gamma greater Cp is equal to Cv. For ideal gas Cp minus Cv is equal to R Mr, by using dou v by dou t is equal to mr by p, dou p by dou v is equal to minus rt by v square. So I'm substituting Cp minus Cv is equal to R. Thermal expansivity, it shows the variation of volume with respect to temperature at constant pressure. Beta is equal to 1 by v dou v by dou t at constant pressure. Isothermal compressibility, it shows the variation of volume with respect to pressure under isothermal condition. Kt is equal to minus 1 by v dou v by dou p at constant temperature. Isentropic compressibility, it shows variation of volume with respect to pressure under isentropic condition. Alpha is equal to minus 1 by v dou v by dou p at constant entropy. Dou p by dou v t is equal to minus 1 by v kt. Cp minus cv is equal to minus t beta v whole square into minus 1 by v kt. Cp minus cv is equal to tv beta square by kt. tv beta square by kt. Energy equation. We know TDS is equal to du plus PdV. du is equal to TDS minus PdV. du is equal to Cv dt plus T dou P by dou T at constant volume into dV minus PdV. minus as minus PdV. C du is equal to Cv dt plus T dou P by dou T at constant volume minus P dV. For ideal gas, PV is equal to MRT. Du is equal to, we will get finally CVDT, valued only for ideal gas. For van der Waals gas, P plus A by V square is equal to V minus P is equal to MRT. Du is equal to CVDT plus P plus A by V square minus P into dV. If we integrate, we will finally get this. TDS is equal to DH minus VDP. DH is equal to TDS minus TDS plus VDP. TDS is equal to Cp dt minus T dou V by dou T at constant pressure into dP. DH is equal to Cp dt plus V minus T dou V by dou T at constant pressure into dP. DH is equal to Cp dt minus T dou V by dou T at constant pressure minus V into dP. For ideal gas, DH is equal to Cp dt. Clausius-Clapeyron equation, it is used to find the enthalpy change associated with the phase change. S is equal to F of T comma V. ds is equal to dou S by dou T at constant volume into dt plus dou S by dou V at constant temperature into dV. For phase change, T is equal to constant, dt is equal to 0, ds is equal to dou S by dou V at constant temperature into dV. ds by dV is equal to dou S by dou V at constant temperature. We know dou S by dou V at T is equal to dou P by dou T at constant volume. For phase change, ds by dv is equal to dp by dt at saturation. Integral f2g ds is equal to integral f2g dp by dt at saturation into dv. Sg minus sf is equal to dp by dt saturation into vg minus vf. We know tds is equal to dh minus vdp. P is equal to constant, this is 0. Integral f2g ds is equal to integral f2g dh by t. Sg minus Sf is equal to Hg minus Hf by Tsat. From equation 1, Hg minus Hf by Tsat is equal to dP by dt at saturation into Vg minus Vf. Clausius-Clapeyron equation. Joule-Thomson effect or Joule-Kelvin effect. T1, T2, 1, 2. First law, H1 plus Q is equal to H2 plus W. This is 0, this is 0. H1 is equal to H2. TP H is equal to constant, inversion curve, cooling region, heating region, positive, negative. TP mu is equal to slope of isenthalpic curve on TP diagram. These are H is equal to C length. Mu is equal to dt by dp at constant enthalpy. Mu is equal to positive, cooling region. Mu is equal to negative, heating region. Mu is equal to 0, inversion point. For cooling, temperature of fluid must be less than its inversion temperature. The maximum inversion temperature of hydrogen is 200 Kelvin. So if H2 is throttled from atmospheric condition, then it will always give heating effect. To get a maximum cooling effect, throttling must start from inversion point. We know dH is equal to Cp dt. Cp dt. dH is equal to Cp dt minus T dou V by dou T minus V into dP. For throttling, dH is equal to 0. Cp dt is equal to T dou V by dou T at constant pressure minus V into dP. Mu is equal to dt by dP is equal to 1 by Cp into T dou V by dou T at constant pressure minus V. For ideal gas, T dou V by dou T at constant pressure is equal to MRT by P is equal to V. Mu is equal to 0 by Cp is equal to 0. Mu ideal gas is equal to 0. For ideal gas, mu is always 0. So if ideal gas undergoes throttling process, there will be no change in temperature. T, P straight lines.